Hi, welcome to this ZP Developer Zone. So I'm calling it this ZP Developer Zone Part 2 because I realised I had overlooked answering a technical question that had come in from a customer, and I'm going to jump into that today. So today I'm going to talk about glucose sensors in a pumped system. So we have a glucose sensor, a glucose sensor, a flow cell, and we're pumping through that flow cell different glucose concentrations. So I'll jump into it. Say I'm talking about glucose sensors in a flow system today. Just to say that I do have some upcoming webinars. We have some on the 22nd of September. I'll just change cameras for a second just to say that at ZP we do make a very revolutionary type of potentiostat. It's a very elegant mechanical system. There's no slots, there's no cabling. You can just take screen printed electrodes and you can essentially insert them in. And you can control it using QR codes, which allow me to go from impedance spectroscopy, for example, to square wave voltammetry just by using QR codes. There's no PC or anything required for this. It's all smartphone driven and cloud enabled, so all the data immediately goes to the cloud. So just to say, we will do a webinar on that on the 22nd of August. It's probably worth saying that most of our webinars, there's always one a month anyway. We'll also do one on wearables. Many of you will know, and I'll go very quickly, that we do have a very good wearables technology. This is a microneedle system for measuring the glucose in the interstitial fluid. It does break the skin, but it does it using microneedles, and it has some advantages over the kind of incumbent continuous glucose monitoring technologies that are otherwise on the market. And we'll talk about that on the 28th of August. And just to say, if you're an academic and you are doing sort of biosensor development using things like these kind of screen printed electrodes, we will have a webinar on the 21st of August. You'll notice that with our webinars, and in any webinar that I've described today, I'll put a link underneath the video as well. But with all our webinars, we do one in the morning, one in the afternoon, because it makes it easier for people to attend. And links, as I say, will be underneath the video anyway. So question number 1 is about glucose sensors in flow. Right, so glucose sensors in flow. So this is the setup. So this is what somebody has. And I will just kind of, they've labeled it anyway, but we have a reservoir where they're drawing glucose solution from. They're drawing it through a flow cell. This flow cell is from Zimmer and Peacock. There's a cable coming out the back, and the cable coming out the back is going to the potentiostat. The potentiostat is probably USB connected to that laptop that's in the image. The glucose sensor is actually in that flow cell. You'll find a link to this flow cell that they're using underneath this video anyway. And then they're sort of drawing the glucose through this pump head and sending it to waste. So I understand their setup. And there's the pump there, and as I say, here's the waste. They're pumping at about 0.9 mils per minute. I might get them to change that, but I think first of all we're going to troubleshoot the data that they have today. So before we start talking about changing this setup, I think we're going to simplify the experiment anyway. So the first thing to notice is this is their signal. At face value, you think, oh, this all looks pretty good. You know, we've got a kind of baseline here of PBS. Then you add 5 millimole of glucose, it spikes up. I was not too worried because I could see here that this is actually going to plateau. So I'm happy with the fact that, you know, it spikes up, but then it kind of plateaus, and this one will also spike up and then it'll plateau. So it's okay to, I say it's okay to have signals like this, but I'm going to talk about this a little bit more. But at the face of it, you know, oh, well, this is working. But there's something curious about this data, and I'm going to dig into that very shortly. So first of all, let's describe an experiment that I do, let's say, or we do at ZP quite often, and we do understand it, and it's a bit of a classic for us. So let's take this generation 1 glucose sensor, and I'm saying that very clearly, generation 1 glucose sensor, because I've seen the part number these people have, and they are using a generation 1 glucose sensor. Generation 1 glucose sensors in here, in this video here, and I'll just hide myself for a second. One of our guys, Andre, is doing a real classic experiment. We kind of call it the stirred beaker experiment. So we take a PBS solution and we put a magnetic stirrer in it. We invert the glucose sensor into that solution and we start to stir. Now we get, for the first 100 seconds, we won't really gather any data because we kind of call this the break-in time. when the sensor's all sort of wetting up. But then Andre will describe in the video how he's adding aliquots of glucose. And this video will be linked to underneath. He's adding aliquots of concentrated glucose, and that causes the signal to step up. And he adds some more aliquots of glucose and the signal to step up. And then he adds more aliquots of glucose and the signal steps up. In fact, I might even, in fact, you can see it happening here. Now he's just letting the baseline settle. I think he may say something in the video about waiting for 100 seconds. And I can see it's getting close to 100 seconds in that video. But as I say, I'll also link to this video as well. And then he adds the glucose and there it steps up. So you can watch that video, because I wanted to say that before you go to complexity, start off with simplicity. So the simplest thing is actually just follow this and see if you can get the same, let's say the same profile of signal. Then we can start actually understanding what's happening in your particular setup. So as I say, if you watch this video, in fact, you'll find that Andre in this video gets some really nice glucose steps. So that will be the video that you will follow almost one for one. When you've done that, you've kind of baselined yourself. You say, you know, my setup works. Now I can start adding complexity to that setup. So I said I noticed something about the data from the start. So at the face of it, things, you know, not perfect, but they look like they're working. But there's something very curious about this. And the curious thing is that this is 0 microamps here. And all of your signals are actually below 0 microamps. So in Andre's video, he's running that glucose sensor at approximately 650 millivolts, and he's getting positive currents. All your currents are negative, you know, and it's not to be dismissed. So I've got a couple of theories around this, and I'll just lay out the theories and then again tell you to do a simpler experiment to start with. But yeah, all your currents are negative. This is super curious. So let's say two theories for this. Auction theory. This is the simplest one. I doubt you're doing this, but we'll, at least we can ask it. Rather than applying 650 millivolts, which would be the potential for the oxidation of hydrogen peroxide, you're actually applying minus 650 millivolts, and you're actually doing the reduction of oxygen. I doubt you're doing this, but it's, you know, but we might as well flag it up because it's a simple thing to check. I doubt it, but let's say, you know, let's flag it up. So there's the auction theory, and I've also got something called the ground loop theory. I'm hoping it's not the ground loop theory, because it's, well, we'll soon find out by you doing a simpler experiment, to be honest with you. In the ground loop theory, you've got a pump and essentially a PC system with a potentiostat on it. And those two systems are actually in contact with each other through the conductivity of that solution. And so you've got one that's grounded and another one that's grounded, and they should be at what's called the same ground. But in fact, if they're at different grounds, you can get the flow of current because you've got two electrical systems actually in electrical contact with each other. Now, I can understand that really the pump head should be very isolated, and you know, it's not a theory I strongly believe in, but we do have to flag it up because there's something strange going on here. If you are applying 650 millivolts, and in fact all your currents are negative, then this ground loop theory could be the reason for it. So let me first of all just lay out the oxygen theory really quick. So you've got a generation 1 glucose sensor. I'm expecting this kind of staircase response. We've built the generation 1 glucose sensor. So, you know, glucose comes in. I say you know, but I'll make the statements. Glucose comes in, it reacts with the enzyme, and we form the consumption of oxygen and the generation of hydrogen peroxide. Now, the hydrogen peroxide is what we're actually detecting. And we're detecting it by applying a potential 650 millivolts positive. Be very careful about that. And you should get some currents in the sort of microamps when you're doing that, because we get this flow of electrons. Now, if you're accidentally, and that actually recycles the oxygen, if you're accidentally applying minus 650 millivolts, you're in fact not detecting the generation of hydrogen peroxide, you're detecting the consumption of oxygen. And that's okay, actually, because Leyland Clark, and I think he's called the father of modern biosensors, in 1956, he invented an oxygen sensor. And in fact, it was an amperometric oxygen sensor. And then in about 1958 or 1959, he then actually just added glucose oxidase to that and made a glucose sensor. You can measure a glucose sensor by measuring the consumption of oxygen. most people, and I can, most people actually don't measure the consumption of oxygen in a glucose sensor. They actually measure the generation of hydrogen peroxide. That's not the point today. The reason I'm only bringing it up is because you've got negative currents. So it looks like you're actually measuring the consumption of oxygen through its reaction with glucose and the formation of hydrogen peroxide. Why do I think this? This is what one of our oxygen sensors looks like. So this is oxygen, an oxygenated solution, about 6 parts per million of oxygen. And we get a current due to the electrochemical reduction of oxygen at about 600 minus 650 millivolts. And then if we scavenge that oxygen, the signal goes close to zero. That's a little bit like your signal looks like. That when you've got no glucose, you had the highest, if I can call it, in magnitude signal. And then as you added more and more glucose, it got closer and closer to zero. So it feels to me like you're actually measuring the consumption of oxygen. So that's my oxygen theory. I will also tell you how to problem solve this shortly. There's also something that's a bit more convoluted, the ground loop theory that I've sort of thought about. I've seen this in the past. You've got a couple of electrical items plugged in. Great, there's no issue with that. You've got the PC. The PC through its USB-C or USB is in connection with the potentiostat. The potentiostat is in electrical contact with a flow cell, and you have a pump system. And the pump system is pulling solution from the reservoir through the flow cell and sending it to waste. This line here means that in fact these two electrical systems are actually in contact with each other. This is kind of ionic contact. Most electrical and electronic engineers don't think about this too much because they're kind of used to conductivity through wires. And they can't imagine conductivity through solution. I don't want to generalize too much, but it is a bit of a strange concept. But in fact, you do have electrical contact through these two systems. Now, I can absolutely understand the whole argument that, well, there shouldn't be electrical contact because this pump head should be very isolated. But if it's not, then this theory could be the case. I'm not defending it, I'm just giving it out as one of the options. If I split this system in two, you won't get ground loop problems if the grounding on this side of the system is the same as the grounding on this side of the system. But I have seen this happen in the past where in fact these two systems are not at the same ground point. If one of these systems has for example, a slightly higher resistance to ground than the other side of the system, then the grounds are not together, they're actually separated. And when they're separated like that, you can have the flow of current. And so you may have a signal that you're applying 650 millivolts and you have your glucose signal. But you've also got another signal that's actually due to this ground loop. And if anything, I'm thinking that the pump is at a slightly higher ground than the actual potentiostat. It doesn't make me right. It just would help me understand why you're getting apparently a negative current when in fact you're applying plus 650 millivolts to that glucose sensor. So my next steps would be this. I've got a video here and I've got a link to the video. I'd say back off slightly, get away from the complexity first of all. Don't do flow cell experiments. Watch the video from Andre and repeat Andre's work. Get to where Andre is, because then you know that my setup's working. When I'm not using the pump or the flow cell, I've got this good signal. Then when you've got that, it's time to go back to the flow cell. But rather than trying to sort of deconvolute or, at the moment, I'm not sure if it's just because you're applying the wrong potential, which I really doubt, or in fact, you've got a ground loop problem. But before we start solving a ground loop problem, I need to understand what the root cause of this is. And going to the simpler testing in a beaker experiment will, if it's behaving the same way as it does at ZP, then that's baselined you that in fact everything is working, and then you can start adding in complexity again. And that, once you build up complexity, you can see at the point at which things break, and then you've got your kind of root cause. So it's a sort of, I'm giving you a strategy here. These are links to the technologies that these people are particularly using. And if you have any questions of ZP, don't hesitate to reach out to us. I will say I'll put all the links underneath the video as well. Okay, thanks very much.